All right, so far we've relied on simple data types like addresses, uints, or booleans. In the previous lecture, we also grouped them together into structs, and I showed you the difference between using smart contracts or child smart contracts as data stores versus structs as data stores. But what if that's not enough and you need to track them in maybe an array-like data structure? Maybe you want to track the timestamp when a deposit happened. You want to track every single deposit from every user. You want to track how many deposits happened and many more details. Just as a rule of thumb, before we even continue with that, it is always better to just store the most necessary functions and informations on the blockchain and do everything else off-chain. But because we want to explain structs and everything, now I will track everything I can and like every single payment, single thing in greatest detail possible with our smart contract now. But rule of thumb, just move the stuff that really needs the blockchain onto the blockchain. So for sake of this example, let's write our small wallet and then improve the small wallet. And it's not going to be the same wallet that you're going to write at the end of this project, but it's going to be just enough to explain how mappings and structs work together. So let's call this, I don't know, example mapping struct solidity. And bring over the SPDX license identifier and the pragma line. And let's call this mapping struct example. Now that I think of it, maybe not the best to have example mapping struct solidity and then call the contract mapping struct example, but just bear with me on this one. And what we want to do is we want to have basically three functions. One is a function deposit money, one is a function withdraw money, and the other function is getting the balance of a particular user. Now, what we did before was a mapping that maps address to a uint, and we called that balance. And then we have a function called deposit money that is public payable, and we are going to balance message sender is plus message value. And when we want to have a function withdraw money, maybe an address payable to and a uint amount public, then we are going to reduce the balance of the message sender by the amount, and then we are going to send the amount to the user. Now that one doesn't track a lot. I mean, we can send money here and we can send money back. Make this a little bit bigger. But it doesn't really track any kind of deposits unless you are going to look into a block explorer and just see when somebody deposited and when somebody withdraw money. And that's something we are going to look into the next project, how we can track that with block explorers and how we can do code verification. But in this lecture, I want to show you actually how to use structs and how to use them in combination with mapping. So why don't we create a struct that actually records a transaction, be it a withdrawal or a deposit. So let's call this a struct transaction. And over here, we are recording an amount and we are recording a timestamp. And the other thing that we are going to do is we are not keeping the balance in a simple unsigned integer. We are keeping the balance in another struct that has the current balance, the number of deposits, the actual deposits, the number of withdrawals, and the actual withdrawals. So let me show you how that can work. Struct, simply call this balance, for example, and maybe the total balance. And then we have a uint number of deposits. And then we have a mapping inside that tracks for each deposit an actual transaction. And then we have an unsigned integer number withdrawals. And then we have a mapping that tracks for each withdrawal a transaction withdrawals. And over here, our mapping balance isn't going to map to an unsigned integer. It's going to map to balance. And let's call this balances. Now, what we can do here now is, instead of just simply tracking that a balance was received, we are going to increase the total balance when a deposit happens, and we are going to record a new deposit in our deposits mapping in our balances mapping. The way this works is by accessing with the dot specific variables from our struct. So in our balances mapping, we want to increase the total balance by the message value, but we also want to record a new transaction. And it happens to be like this transaction, and we want to keep this in memory here. It's going to be a deposit, is a transaction that is containing the amount, the message value, and the current timestamp, which is the block timestamp. And then we are putting this on the current position of the number of deposits, and then we are increasing the number of deposits. So if it's the first one, number of deposits is 0 because it's initialized with its default value. We can simply use this in an array syntax writing to access our mapping keys. So what we want to do is from the balances of the current address that deposits, we want to get the deposits mapping, and over here we are going to access the balances message sender.num deposits, and we are going to assign this the deposit, and then we are increasing the number of deposits. Message sender num deposits ++. Okay, just to be clear, what happened here is we want to write into this mapping with this key type, or with this key, with the value of this variable for this key. So over here we are expecting an unsigned integer, and that one in the first time we call it is 0. So what actually happens here is that this one will be 0. So we're accessing the first element of the element with the key 0 of the deposits mapping over here. And this one expects a transaction. So we are going to save this transaction over here in the deposit 0. That's our first transaction. And then we're increasing the number of deposits. So the next time we call deposit money, that one will be 1. So the next time we deposit something, we are going to access the deposits variable 1, and so on. So now we are going to do the same thing with withdrawals as well. Let's just head over down to the withdrawals. We are decreasing the balances of total balance by the amount. And then we are also recording a new withdrawal. So a transaction memory withdrawal is a transaction, and that is the amount and the block timestamp. And we are going to add this to the balances of the message sender dot withdrawals. And over here we want to access the key of the num withdrawals. So in our balances, message sender num withdrawals is the withdrawal. And then we're increasing the number of withdrawals. Yeah, it's quite extensive here. Let's give this a try. So we are going to deposit one way over here. Oh, we should have made this public. Then we can actually see what's going on. Let's try this again. So deposit, and let's see what happens here if we're gonna copy this address. Okay, we have a total balance of one way, and we have the number of deposits is 1. So we had 1 deposit so far, but we have no way to actually access the deposits. Question is, what happens if we make this one public over here? Does this work? No, it doesn't. So we have to write specific getter functions for the deposits. So let's say we want to access the deposits for a specific address, then we have to write our own getter function. It's not getting returned automatically. So if you're gonna get deposit number, and then it's like uint deposit address from uint deposit public view returns a transaction. Memory. Okay, and here we're gonna return balances from deposits num deposit. Let's see if that works. So I'm just gonna clear this out. I'm gonna deploy this again. And let's deploy, let's get one way into the smart contract. And let's see if we can copy this address over here, balances. So we have 1 total balance, 1 number deposit. And now we want to get from this address the deposit with the index 0. And we get back the amount and the timestamp. And that is the amount is 1 and the timestamp is this Unix timestamp. Now, there are a couple of things that are important to understand with mappings. And I think the most important thing to understand is a mapping doesn't have a length, unlike arrays. So with an array, you have a length. And because an array, it's known to the smart contract or known to Solidity how many elements are stored in there. The good thing and the bad thing with mappings is they don't have a length. So every value that is possible is already initialized with its default value. And why is that? That is because internally it is stored with the actual hash of the value that you provide as a key. And it will just look in its own storage and see if there is anything written there. And if not, then it will just return you the default value. So this is also where we actually have to keep a number deposits and number withdrawals helper variable to understand how many deposits were actually there. If you do this with an array, then you can do the length, but an array has other drawbacks. And yeah, they're just not as convenient as mappings. Yeah, and that's it. What I wanted to show you with structs and mappings. They are quite powerful, and you basically will use them almost everywhere. And I've seldom seen smart contracts that do not use structs and mappings. And with that, I want to go to a different concept now that are exceptions.